that. Cool. Yeah, so my name is Clark Boylan. I work with Jim and Anita and Liz and some other folks to help run the OpenStack CI and developer automation infrastructure. Basically, what we do is make sure that the developers of OpenStack can do their job and every 6 months cut a new release of OpenStack and build your clouds. It's actually kind of a good thing that I'm going after Jim, even though it didn't occur to me until this morning. Jim kind of presented the in a perfect world vision of how we do CI. And this talk is actually going to deal with, what do we do when things go wrong? How do we deal with the fact that tests do fail? And so it kind of is a nice segue from Jim's talk to that. I'm not going to talk a whole lot about OpenStack itself, since I run the developer automation and CI for it. I'm not the expert on the compute and networking and storage and so on. There's other folks that do that, like John, who was in here. There he is. And can speak to that more than I can. But I do need to give a little bit of context to what it is that we do and why what we do is what I think interesting. So OpenStack is open source software for building public clouds and private clouds. You can download it from Git, our Git repos, and go run it on your, your laptop. You can have a full running cloud on your laptop. It might be kind of slow, but it'll work. It's important to know that OpenStack is made up of quite a few projects that are interrelated. And when you run them all together, you end up with a running cloud. So it's not like one daemon that you run on one machine and you've got this running cloud. You've got many of these processes that might have multiple daemons running across many, many machines that give you this cloud. And I think, what are we up to, 20-ish? There's quite a few of them, and we keep adding them all the time. So we've got Trove and Ironic and Marconi that are kind of going through the addition process, and eventually will be part of that core system. So what does this look like when you deploy it? It's kind of complex. As you can tell by the diagram, there's things interconnected all over the place. And this really illustrates the complexity of running a cloud. You've got your storage and your networking connected up to the compute and so on. But it also illustrates that there's a lot of these daemons all running and talking to each other. And so when we test OpenStack, we're running the cloud, doing full integration testing. You end up having a lot of these daemons running, collecting, and generating logs that we then need to go through and post-process and determine, why did something fail or why did it pass and so on. And there's a lot of that going on. So the CI environment. We run tests on all proposed patches. You write some code, you push it up to our review system, we immediately test it. And we do that so that we can provide feedback to the code reviewers as well as the person submitting the code. We want that to happen as quickly as possible so that things can get fixed and improved and iterate quickly in the development process. We do everything from static code analysis, like PEP8 and linting, to unit tests, which run within the individual projects themselves, to full-on integration tests, where we deploy a complete cloud in a single node, but it is a full cloud, and then run a test suite against that. We also gate code merges on these tests, which means that if your code doesn't pass the test, you don't merge. You have to go through that testing period again, pass all of the tests in order to merge. We call that project gating. We do this because it helps ensure code quality. If we're only ever merging things that pass, the trunk or the master branch or whichever branch stays clean and it continues to work. This is good for developers because they can grab the code at any point in time and start hacking on it and don't have to worry about, is this the branch that's supposed to be working? Do I need to be reverted back to some point in time where the test passed and so on? And it protects the tree. This is important for people doing continuous deployment. Again, just like developers, they should be able to grab our code at any point in time, deploy the thing, and it should work. But it also means that we run tests continuously, like a lot. For the Havana feature freeze, which happened right around here at this peak, we were running 10,000 jobs a day in Jenkins. And that continued on as we went through the rest of the release process. It kind of petered out, but we were still running thousands and thousands of tests per day. This is interesting to us because it generates a lot of test results. We have this giant data set of log data from the testing system that we can go through and then kind of hammer to find out, is the code getting better? Are new bugs being introduced? And so on. So typically, your test results or have a binary result state. You passed or you failed. This is what Zool reports back to the code review system. And so the person submitting the code and the person reviewing the code, they see, OK, test X passed, test Y failed. That's good. It kind of gives you, it's very quick and easy to see what happened. OK, test failed. We need to go figure out why. But there's a lot of log data that we're generating, especially for these integration tests. Right now, so this was about 2 weeks ago when I checked, we're generating about 366 megabytes of uncompressed log data from every integration test. And from that, we should be able to determine a lot more than just pass or fail, especially in the case of failures. We should be able to say, hey, this failed because of this bug, or this failed because of this particular known issue. We can do a lot more than just say, hey, your test failed, go fix it. The way these logs are presented to the developers, at least before we started this work to process the log data, was through an Apache file system fronted by Apache, presenting auto-indexed files. So you'd get a comment from Jenkins saying, hey, your test failed. Here's a link to all of the logs. That's really clunky to deal with. It's 366 meg. As a developer, you don't really want to have to go digging through that, especially when you've got 20 different changes in flight that all need to be, juggled through the code review system. And it's not indexed in any other way than what Apache's doing. So it's kind of hard to say, OK, show me all of the jobs that failed in this time frame for this project, and so on. So there's a lot of data there, not a lot of information. Some folks had written wget and curl scripts that just went and kind of grabbed everything, and then they were running crazy regexy stuff locally, and not user-friendly.
Are they still doing that, or is that mostly stopped?
That's mostly stopped. Now, that setup would be fine if failures never happened, right? If we always said, oh, these tests passed, we wouldn't really care that we had so many logs. We could just kind of ignore the fact that they exist because everything's happy and moving through. But the truth of the matter is that failures happen, and they happen a lot. And it's often not the fault of you, the developer. It's someone else who's come through and there's bugs, basically. And they're the 1% failures, the race conditions or underlying hardware exposing particular problems where your tests get run and they failed and it had nothing to do with you. That's painful. So a lot of what we've done is trying to help developers where they know their code is good or they've tested it locally, it passes, that are running into problems that exist previously in the system that need to be fixed in order to get the test to pass. The first attempt at this was basically we said, well, just rerun the tests. And you can do that with a recheck review comment. So in the code review system, leave a comment that says recheck. And the code CI system would say, oh, I need to go rerun the test for this particular thing. And what we asked folks to do is to attach a bug number to those recheck comments so that we could track the bugs associated with the particular failure, right? The developer is asserting, I'm not at fault here. This bug is at fault. Please go sort that out. So we're manually tracking this bug to failure relationship. There's a lot of human overhead. They have to go digging through the 366 meg of log to figure out, OK, which bug did this? OK, now go back to Launchpad, find the bug, and then go write this comment and associate the two. It also results in incomplete data. Not everyone's going to do this for you. Some folks are just going to ignore it, or they're going to push new code, and the tests are going to run again and possibly fail again for other unrelated reasons. And this is prone to errors. People get things wrong. There might be innocuous warnings or debug lines in the logs that folks associate it with a problem, but they're benign. So what we found was this recheck list that we were building from these code review comments was just not sufficient to actually figure out what bugs were in the system and get them out. And we can kind of see an example of this. This one's fun. So this one actually is a really bad bug, and it's getting rechecked a lot. But the way we presented the data to folks was, when was the first time we saw this problem? When was the last time we saw it? How many times have people rechecked with it? And then here are all the changes that were affected by that particular bug. But the system was scoring this really bad bug lower than these other two that were probably not a major problem for the whole system of OpenStack CI. Notice there's only a handful of changes being affected here compared to this, and the scoring is done by number of occurrences, when they happen, and so on. And really wasn't helping get the bugs out of the system. So we needed something different. Ideally, the logs would be accessible. Hitting Apache and getting 366 meg of log isn't really an ideal way to go grepping through them. It'd be also great if whatever thing was in front of the logs had a REST API. A lot of our developers are hacking on systems that present REST APIs. They're familiar with them. They're happy coding against them. So it was a feature that we wanted to fix this problem is, hey, let's throw a REST API in front of it and see what folks build. And then also a query language. So I was talking earlier, people had these wget scripts that then did crazy regex stuff. It turns out you can do a lot of nasty stuff with regexes, and none of it's going to be consistent from one person to another, and that's just really clunky. So we thought it'd be actually really handy to have a common query language so that everyone could speak the same thing when saying, hey, let's go look for this problem or this other problem. We can do it the same way and understand each other. But then going back to that architecture diagram, there were a lot of services. They all, well, not all. A lot of them log in different formats in different ways. And so we also needed a way to take these logs and kind of transform them into a common schema, especially if we were going to query against them. So we needed a data pipeline where we could do things like flatten into this common schema, transform, maybe add data, filter it, and so on. So go hunting around looking for things that would do this. There's actually quite a few options that have been suggested or I found. FluentD is really good at moving things around. Hadoop is really good at doing batching, lots of data processing. Splunk is kind of, sort of, I don't know, I think you get for free 500 meg of index data, which is, that's a job and a half. And there's a bunch of other options. Jenkins actually has some plugins that you can run that based on regexes can tell you, oh, hey, this thing happened. And so yeah, there's options. We ended up going with Logstash, Kibana, and Elasticsearch. Biggest reason being that it had a lot of these features that we wanted going in. The whole pipeline is open source. They're all Apache license version 2. Kibana is a really great simple UI for lots and lots of data, which means we could put it in front of our developers and they could just go crazy and start searching through it really, really easily. But then there's a REST API in front of Elasticsearch, and I think that's really kind of the really killer feature that we've got. Again, our developers are really comfortable working with REST APIs, and we basically said, here's a public REST API endpoint to all of this data. You can query it however you want, have fun. And then Elasticsearch presents the Lucene query language as its, to query through its data, which is handy again because it's consistent. Everyone can talk on the same page and understand each other. And Logstash gives us a flexible data processing pipeline. Basically, you can have a bunch of different inputs that then get mutated in the middle and then spat out in a bunch of different outputs. Everything from you can input from standard in, TCP, UDP, syslog, lots of options. You can mutate things in the middle. You can remove, add, and so on, and then spit out in a bunch of different formats, things like Graphite, Elasticsearch, and so on. Things that are important for us are flattening these disparate events into this common schema. Again, because we've got logs coming from syslog, we've got logs coming from Nova, we've got logs coming from Swift, Apache. They're all in different formats, but we want to query them in the same way. I don't want to have to think, is this data in Apache format? Is this data in syslog? Whatever. I should be able to query them the same way. We also want to be able to combine related events. So, a stack trace, that might get shown up as 10 different log lines or something. We need to be able to combine those together as a single stack trace so that we can look at it as a single entity. And then filtering noise is actually important. I'm going to talk a little bit later about how we can't index everything. So filtering is really important. And then we can annotate events with additional information, which is really cool. At the end of the talk, I'm going to talk a little bit how we're doing statistical analysis and annotating every one of these log lines with some information about whether or not we think it's odd. And then we can do this mostly in real time. Typically, data can get completely through the pipeline in about a minute or less, which means that if your tests fail, within a minute you should be able to go through and search for why that happened. but everything's not so rosy. I started working on this back in April, so it's been almost a year. And the initial start was really, really slow and clunky. In a typical Logstash, Kibana, ElasticSearch setup, you'll run a bunch of daemons on your hosts that collect the logs from wherever they are. This will then talk to a Redis server that becomes basically a big funnel. And then that talks to a single or a handful of daemons that then do additional processing that do your outputs. This doesn't scale very well for a couple of reasons. The first being, I don't want to be running daemons that are trusted on our untrusted Jenkins slaves. These Jenkins slaves run tests as root sometimes, or with root privileges, that can basically do whatever they want. I don't want them to be able to talk to a trusted privileged area of our CI system. And so I need to be able to way to detach the trust that we've given in these slaves, however little there is, from being able to add data into this ElasticSearch and Elasticsearch Logstash cluster to solve. I'm going to talk about how we solve that here next. But then Redis. Redis was this giant funnel. I don't know if I just don't know how to deploy Redis properly, but I could not get it to work reliably at the scale that we're going, and it just wasn't worth it. So that was one of the first things I did. I got rid of Redis. And then it's impossible to index all of your logs. At 366 meg per test, 10,000 tests per day, there's a significant amount of data there, and we're running all of our CI infrastructure on donated cloud resources. So I don't want to go and just build like a 200 node cluster to deal with this. I want it to actually be kind of nice to our cloud providers. So to deal with the Jenkins slaves being untrusted and needing to get data from them, I wrote a Jenkins plugin that spits out Jenkins events over the 0MQ pub sub, which allows us to attach log workers, little like 120-line Python scripts that listen to these pub subs and then can process logs once they're available. So that's on the plugin index. You can click the button in Jenkins and install it. And it basically just emits a bunch of Jenkins build events on the pub sub. To get rid of Redis, I basically attached on the other end of this 0MQ pub sub a Gearman client. So this Gearman client goes, oh, a job finished. Let me then submit a bunch of jobs to the Gearman server saying, process this log file, process this log file, process this log file, and so on. And what that did was it changed the Redis queue from being one item in the queue per log event to one item in a Gearman queue per log file. And that reduced the size of the queues tremendously and made the whole system much more stable. And then we filter extensively. Very quickly, we decided we were just going to ignore all log lines at debug level or lower, just because that was a significant portion of our log data, and it wasn't really useful usually. The log archive is still going to have that data if you need to go back to actually debug particular problems. But for searching through and determining why things failed, it actually wasn't as helpful. And when it is, we've decided to treat those as bugs in the software. If there's a bug in your software and it's only caught by debug lines, we should probably have better logging. And this is what it ended up looking like. So we've got Jenkins slaves off on the right. They're connected to the Jenkins masters via SSH. They run jobs. When the jobs are finished, the Jenkins masters actually, via the SSH connection to the Jenkins slaves, copy the data from there to our log archive over SCP. And that's just using built-in Jenkins plugins. So we've got a somewhat secure data path from the Jenkins slaves to this log archive where we're storing the data. Then the Jenkins masters emit 0MQ events saying, hey, a job was finished. This Gearman log client picks that up, submits a bunch of jobs to the Gearman server saying, please go process the logs associated with this job. And then a bunch of Gearman workers then go grab the logs from the log archive, shove them into Logstash indexers, which do much of the work, actually flattening the data, annotating it, and so on, via TCP. And that's all local, so it's super simple. It's a TCP stream, and it's line delimited. And then Logstash is nice enough to then output all of this data into an Elasticsearch cluster. And it actually works really well. And And one of the reasons for this, I think, is, I don't know if you've noticed, but every single one of these kind of items here is horizontally scalable, except for currently the log archive and then the Gearman stuff, or at least the Gearman client and server. So as load grows, as things get more complicated, we can just scale out. And we did that this week with the Jenkins masters. We went from 3 to 5. We do that every day with the Jenkins slaves. We run anywhere from like 100 to 500 slaves at any one time. And then we've also fiddled with different sizes in the Logstash processing pipeline and the ElasticSearch cluster. So it's really handy to be able to do that. You want to be able to scale out, especially when you're using donated cloud resources that might not be super performant. But that's OK, because we just add more nodes. So what has this given us? That's numbers from yesterday around lunch. 1.2-ish, 1.3 billion log events were indexed at that time from 72,000 jobs. And they're all queryable through a public REST API or through the Kibana web UI, which is great, because it means people can build tools like ElasticRecheck. So ElasticRecheck is a tool that Joe Gordon, Matt Trainish, and Sean Degg have put together that listens to job failure past reports. And when jobs fail, it says, hey, let's go find out why that happened. This is tied into kind of the recheck system we had before. But instead of having people manually decide which bug caused the failure, they use bug fingerprints to discover occurrences of bugs. You basically write an ElasticSearch query that says, if you see this in the log, this test failed because of this bug. And it automated that previous manual step of mapping bugs to failures, which is great because it makes it super accurate. After we'd done this, we noticed that a lot of the data in the old recheck list was not very accurate. People were misclassifying things, or things were just getting missed altogether. And this picked up on it really quickly. So now we have a different list. Well, I guess we have both two lists. They're up concurrently. But notice that bug from before, 1254890, it's now at the top of the list. We're sorting in a different way. Now we're sorting by the total number of occurrences over time. So we get hit by this one a lot. It's at the top of the list. But we also give the developers looking at this links back to the Logstash web UI and to the bug in Launchpad. So from this one place, you can find out what the bug is, how many times it's occurred. You can then dig through the logs in a much better way. And it's really, really accurate. Again, it's identified this bug is actually more important than those other two that were before it previously.
What's the linearity on that? Because like, I can't read from Vicky down the bottom. I can see with its dates, but I can't quite.
So it's 2 weeks along the bottom of days, and then up to 12.5. So 12-ish, from 0 to 12 from the y-axis.
So it's probably a couple hours from each data point?
Yeah, I'm not, Jim, do you know? Oh, sorry, the question was, what is the granularity on this? What x and y-axis, what kind of granularity we have there? And it's. Yeah, I
think it's 1 or 2 hours.
OK, and along the x-axis is about 1 or 2 hours for every point, and then from 0 to 12.5 on the y-axis.
The y-axis changes based on the bug, so some of them have more than
Right. The y-axis scales based on the number of occurrences. So here on bug 1253896, we go from 0 to 8. So it's based on the number of occurrences that happen. ElasticRecheck will also go comment in the code review system when it's found the reason for a failure. So no longer do you need to actually go do anything. If you're a little bit patient, wait 5 minutes after the failure happens, there's a good chance that ElasticRecheck will come back to you and say, hey, I noticed the Tempest failed. I think you hit bugs, blah, blah, blah. And you can recheck with that bug number if you want, which is really handy now. As a developer, you can spend a lot less time digging through logs, and you can rely on this great tool.
Question.
Yeah.
So if the expectation is ElasticRecheck says this is the bug that you hit, why doesn't ElasticRecheck just automatically recheck it?
OK, so the question was, why isn't it automatically rerunning the jobs for us, or automatically providing this recheck comment? And that's because when we first started this, I think we were a lot less confident in how accurate it was going to be. We probably need to have a discussion soon about whether or not we can make it automatic. I know initially we were worried that OK, maybe some things would be too generic or so on. So I think we're hoping that people will still actually think a little bit about whether or not this applies. But in practice, I don't think many folks are, and it's working well, so we might need to revisit that. I guess before I go on, it'll also report to IRC channels, which is kind of nice to see overall trends.
But
So,
also kind of depressing.
yes. The comment from the audience was they're also kind of depressing, because you just, if you're watching the channel, you're constantly getting pinged by this bot saying, hey, this happened, this happened. And the reason we have that is because in reviews, if you're not looking at it's hard to look at all of the reviews and all of the comments, and so it's really good to kind of have a line by line, just, hey, this happened, this happened, this happened, to keep on top of what's going on. Real time. So this was really beneficial to Havana's release process. Oh, sorry, the question.
Just wondering, does anything happen on the Launchpad end to say, hey, this is blocking this change, or potentially blocking the change?
So the question is there anything happening on the Launchpad end that saying this is blocking this change? Right now, no. There's no direct tie from ElasticRecheck to Launchpad. Usually folks will go to the bug and put in kind of the data that they've figured out from ElasticRecheck. But I think that would make the bugs really noisy. But it's something that we should probably look into, is can we sanely leave notes in the bug itself? So yeah, this was beneficial to Havana's release process. We released Havana back in October or November last year. And right around feature freeze, the gate, the queue that was running all of our tests for merging, it was, I don't want to say unstable, but it was hard. It was having throughput problems. Lots of tests were failing, causing things to get kicked out and needing to be rerun. And that was right around when we turned on ElasticRecheck. And it helped us identify a lot of specific race conditions that we could then prioritize fixes for to actually do a release. And that was really, really helpful to say, this, and this happen a lot. The real problems in the code, let's fix them so that we can do a release. Cool. So the problem with ElasticRecheck is you still need a human to determine what the bug fingerprint is. Someone has to go at least once, read through the 366 meg of log and figure out why this failed, and then write a query for it, and then submit that to ElasticRecheck. That's often a lot of work. It's not a simple thing sometimes for some bugs to figure out, what is the actual trigger of this failure, and that, so that's difficult. Why can't we just have computers do that for us too? I mean, that'd be kind of cool. So, and Sean wants me to say that this is still very much a goal. We're not there yet, but it is running, and it is giving us interesting data. And what we've done is we're running the log events through a spam filter, basically, CRM 114. And it then classifies every log line as being like a success log line or a failure log line. That's kind of cool. Now you can have a probability that, hey, this thing relates to a failure, this thing relates to success, which will help you, hopefully. The idea is to identify very quickly fingerprints for particular bugs. You can just query ElasticSearch, say, give me all of the things within this probability range for this particular test, and give me that data. The way that works is it's using an orthogonal sparse bigram classifier, which is a mouthful. It's a variation on a Markovian classifier where it takes a 5-word window and it constructs unique word pairs and then creates a statistics file saying, this is how often these word pairs happen, which allows you then to go back and look at the probability that that word pair maps to success or failure. This is kind of cool because it's lightweight and fast when you're using unique. Because they're unique, you end up with a small statistics file, and it's only 2 word pairs, so it's pretty quick. Then CRM 114 basically looks up the probability any given phrase is in a class, success or failed, based on a Bayesian chain rule. So statistics is not my background, so this stuff isn't, I kind of get what's going on. Now, you have to train it. It's a machine learning thing. We've decided to go ahead and train it on everything. Jenkins is already pre-classifying whether or not the log data belongs to a success or failure class for us. So we can kind of, without thinking much about it, have CRM 114 train the data in the right class depending on what Jenkins said. One of the interesting things that seems to be occurring is that because there's 366 meg of data, for these integration tests, and the logs are very similar between failures and successes, is that CRM114 seems to be identifying things almost like a probabilistic diff. So if you things between one and the other, it's kind of showing you the diff between the two, which is kind of cool. And so the results. So what does CRM114 spit out? It's returning this PR value, which we then negate on logs for failed jobs. But this PR value is the log base 10 of the probability that any log event is in a class, less the log base 10, the probability is not in the class. So it's normalizing these probability numbers for our human brains. The reason that CRM114 does this is that apparently a lot of the probabilities end up having like 59s, and so seeing the difference between 59s and 45 nines is not easy. And so they normalize that down to this, which gives you a range of about -304 to +304, which is a little bit easier to look at. On positive error PR, success is going to be greater than 10, meaning a strong correlation. Sorry. So success is positive, failure is negative. Anything beyond -10 or less than, greater than -10 or less than -10 is a strong correlation. So we can actually just query for that. Give me all of these things outside of this range. And so we can do that. This is what an ElasticSearch query looks like. We just say, give me, and I've given it -1000 to -10 just to catch any stragglers. It's actually depending on your floating point implementation. So it may not be 304 to 304. It could vary. And when I did this is what it found. It found this error line from a Neutron DHCP RPC agent, blah, blah, blah. It couldn't do whatever it wanted to do, and then the error PR value was -12. So it is finding stuff for us that is relevant to why tests failed. But this isn't something that we could use as a fingerprint to feed back into ElasticRecheck. So we need to do a little bit of work there to take this into things that classify the bugs for us.
So those sort of things are spit out of automatic processing of those 366 megabytes?
This is. And then that's actually just verbatim what was in the log file.
So how did you find that particular log line?
I queried that query at the top, error PR from -1000 to -10.
Oh, and that's
and
an error log line? Is that
yeah.
It just says, here's the log lines that are strongly correlated with failure.
Yep, exactly. So the question was, how did I find this log line? And it was I literally just ran that query in quotes above against Elasticsearch, and it actually returned a list of things. This wasn't the only item it returned, but I kind of grabbed this one. Looked cool because it said error. But it does seem to be actually correlating things that are at least related to failures, maybe not strong enough for fingerprinting a failure, but it's a hint. It's getting you closer to that, why that happened. And so that's really cool. And it's really simple. This is literally the program that we're running in CRM114. I forget how many lines. I've stripped out the comments and unneeded white space, but let's see. Yeah, there we go, fits. That's literally how much work it takes to do what we're doing. And all it's doing is it's saying, go line by line, remove any timestamps, because we don't need to train on those. Learn in the right file, then classify this data. Do a match against the results. It's a regex string parsing language, and so to actually see what data you got, you do a match against the string it returned. Grab out of that the result, the probability, and the PR value. If the match was a failure, we're going to negate the value of of result, and then we're going to output result as PR. Is that what's going on there, Jim? Pretty sure. But that's all it takes. CRM114 makes this easy. It's pretty simple. Oh, and I guess I should point out, the OSB here is where you state you want the orthogonal sparse bigram training method. The unique there means pick unique word pairs. So it actually ignores non-unique. It only treats, it only looks at every unique thing once. And microgroom will actually remove from the statistics file old data. So you don't kind of grow without bound. It's cleaning up after itself. So where do we go from here? There's lots and lots of ideas. I think this is still very new. I think we need to make it more robust and hopefully get to the point where we can say, from a query, here's a bug fingerprint, and go on from there. And to get there, we might have to try different training methods. Maybe it isn't as efficient as we think to train on everything, because maybe Jenkins is wrong. And we also tried different classifiers. CRM 114 comes with 6 or 7 classifiers that do better with different sets of data. We started with the orthogonal sparse bigram classifier because it's really, really fast. It's cheap to run. But if we get better results from a different classifier, we can scale out the data processing pipeline and go with a different classifier. Sean Daig has talked a lot about presenting the data to users. We need better UIs. So we've got that ElasticRecheck list. That's a good start, but we can do a lot more in helping present the data to the developers so that they can prioritize their work. Trying to think of other good. What else was there? And ideas keep getting thrown around. I think it would be great. Oh, sorry.
So currently, if you had a failing test, would there be an easy place to go to say, show me the errors in the logs for this failure?
Yeah. So the question was, if there was a failing test, is there an easy place to go to see the errors from this failure? And there is. Why don't I finish up here and then I can kind of do a quick demo-ish thing, assuming the Wi-Fi is working. I think it would be kind of cool to get people with more of a statistical and mathematical background looking at this data. I think it's all public. Anyone can hit this. And so we're very open about it. And I think it'd actually be kind of neat with people that know what they're doing to hit it. But that's kind of selfish, right? That's because I don't want to do it. So yeah, questions. Why don't I go ahead and do the quick demo-y thing first. Yay, all my logs. So is this a failure? No, it was a success. How does that look? So this is the Kibana 2 web UI. It's on my list of things to do is upgrade from Kibana 2 to Kibana 3. That hasn't happened yet. Well, if I do that, we'll have a little bit more room. Perfect. And basically, right now it's showing me all of the data from the last 15 minutes, or there's 474,000 hits. So it's showing me a subset of all of the data from the last 15 minutes. And then there's a histogram of how many hits there are over the last 15 minutes. But if I click on individual log events, we can see things like when it happened, the version of the Logstash schema, the build change. So that's the particular change that caused this log data to happen. The name of the job, the patch set corresponding to the change, the queue that this was built in, the build ref, so the git ref that was used to run this test, and then the build status. So this is where we see, was this a success or failure? The build UUID, the error PR value, so this was inserted in the data processing pipeline by CRM 114. The file name, so which particular file did this come from, and so on. There's a lot of individual data associated with every document here. But we can do things like build status failure. So now I'm seeing lines from failures. And we'll see one of the log lines is, hey, you failed. So you can restrict to things that are associated with failures. You can also do, I think it's log level error. Whoops, that's not it right. There. So I've just asked for everything, that was a log level of error, and here's the traceback that we get. We see that the log level value is error here. And then you can restrict by adding additional stuff. So we can say end build queue gate. So maybe I only want to see failures in the gate. And you can go down to a particular change, patch set, build UUID, and so on. So you can really kind of quickly get down to the nitty-gritty. And it's fast. I don't have to grep through 366 meg of log, wait for it to download. I just ask ElasticSearch through Kibana to give me the data, and it's there. So cool.
Just thinking there could be some interesting links that you could put in the messages from ElasticRecheck.
Into the
message that it puts into Garrett,
mm-hmm.
just basically saying, here is a link that shows you all of the things that look like errors in the logs for this.
Yeah, so the comment from the audience was that when ElasticRecheck comments in Garrett in the code review system, it can leave a link to a query like this saying, here's the interesting stuff you might be interested in. And that's actually a really good idea. I think that's something that it would be easy to implement and would help tremendously, especially for getting people's feet wet in a tool like this. It is simple to use, but if you don't know what's there or how it works, having a little bit of a start is helpful. So,
Very, very cool.
let's see. So I guess the questions? Any other questions that folks might have? I should note, when I first started this, I don't know how much time I have.
You got about 4 minutes.
4 minutes.
3 minutes.
When I first started this, I tried indexing everything, and it caused the clusters to fall over constantly. Because you do a query, and they'd load so much data into memory, everything would and so I found it was very important to be specific about the data that we thought was important ahead of time, just to keep it manageable. So yeah.
So just kind of how long did it take you to get from having the idea of doing this to where you are today?
So the initial idea was in the San Diego OpenStack Summit, which is in October 2012, was that we needed something. We didn't know what it was going to be yet, but that was the initial idea. And I didn't actually start working on it with a lot of time until April of last year. And then it was only a part-time thing. So you probably could have had something like this in a few weeks to a month if you actually spent a full time working on it. Is that it? Oh, question.
What sort of things do you send to Graphite? Or do you not send anything?
So the question was, what sort of things do we send to Graphite? Right now, I'm not sending anything to Graphite from Logstash. We do have a Graphite, and other tools are sending data to it. What I found the power of the ElasticSearch plus Logstash Kibana system is it's very flexible. You don't have to know what data you want to look for until it's there. Whereas with Graphite, you need to have very specific, like, this is what we're going to log, as time trend metrics. And so we just have tools already doing that. And the power in this is being able to just write ad hoc queries and say, okay, show me the things that we didn't think about before. So, yeah.
Perhaps a follow-up to that. I'm talking to somebody online who's watching a live stream.
Mm-hmm.
I want to know how it can be used for generating trend data, or can it?
It can be. Well, so one of the examples is the, so the question was, can it be used to generate trend data? Status.openstack.org. And it can be. Come on. Of course, will it load? So at the top here, we've got trend data based on Graphite. So things that we already know we care about. And then below that, we've got the trend data based on, I guess, we are generating trend data to generate these graphs, right? This is a metric over time. And does that answer the question?
We have time for one more question.
Yeah.
How long did it take to train the CRM114 on all the logs so far?
CRM114, so we just kind of threw it in there. And within about a day or two, we were seeing results that seemed to be useful. So it wasn't very long. And part of that is we're doing like 10,000 events a second when we peak. And there's a lot of data getting passed through it, so it can learn pretty quickly, I think.
You can take another one. Still have a little bit of time.
Okay.
You're pretty close to automating user troubleshooting answers, no?
Sorry,
If someone has a problem, maybe you could have the same kind of database and automate the answer on the mailing list.
yeah, so the question was, or the comment was, you could have, automated things to the mailing list or questions. You could do more with this than just bug correlation within, changes. And that's true. So one of the ideas I think, far out is, I've already written Logstash filters and things for OpenStack logs. people can grab those and use them in their internal clouds. But then maybe we can share CRM114 CSS files or whatever ending format we have. And this is the same stuff that's running in people's production clouds. So we should be able to just kind of copy and paste and make use of the data. Now, people may not want to potentially expose their internal stuff. I don't know, because there is statistical data in there, they might give out information they're sensitive about. But we could, in theory, do stuff like that, share it among other folks as well. So.
Good. On behalf of the LCA team, thanks, Carl.
Thank you.